This is section 2.2 in our book, the derivative at a point. So from our AP Prep days, we know that the average rate of change of a function f from x equals a to a point a little bit away from a plus h, is given by f of a plus h minus f of a all over h. This we call the difference quotient. The instantaneous rate of change, which is a calculus topic, is called the derivative. It's known as the derivative, and we say the derivative of f at x equals a is given by f prime of a is equal to, and then it looks exactly like the difference quotient with a very important difference. We add in this limit. The limit as h goes to 0 of f of a plus h minus f of a all over h. If this limit exists, we say that f is differentiable at x equals a. F is differentiable at x equals a. Trying to expand your vocabulary here. So graphically, what we have going on here, let's compare these a little bit. So graphically, suppose we have a generic function over here. So there is our function f of x. And here's our point A, and coming up here gives us a y value of f of a. And then we move away a little bit from a. So here, this is going to be h away from a. That makes this point be a plus h, and that's going to make its y-coordinate be f of a plus h. So what we're seeing in the case of the difference quotient is that we are taking these 2 points on the curve, 2 distinct points, and we are looking at the slope of the line between those 2 points. That's what we're getting from our difference quotient. Then what we're saying in the case of the instantaneous rate of change is now we're going to push that h and make it go smaller and smaller. And so as we do that, that tangent line moves and it goes from here to maybe a little closer. We move that point in closer and closer until ultimately what we get is a slope of a tangent line. So another name for this, the derivative, the instantaneous rate of change, and the slope of the tangent line. Those are all synonyms. They're all equivalent. So that's the slope of the tangent line, 2f at x equals a. Okay, so let's see what we can do so far. We can find the derivative. So we can find the derivative of f of x equals tangent x at x equals pi, and we're going to do this numerically. So this is actually, we'll learn that our calculator has a way of doing this. We're going to use our calculator to do this. So what we're going to do is imagine taking, then, according to our definition, we're going to take tangent of a, which is pi, plus h, and we're going to have to decide what we're going to use for h here, minus tangent of pi all over h. Now we can't, on a calculator or numerically, take that limit as h goes to 0. So we can't do that on our calculators. So the way instead, what we're going to do is choose a very small h. So we don't have any direction, but let's choose h to be decimal point 5 zeros, 1, 2, 3, 4, 5 zeros and a 1. So that's a very, very small h. So that's going to lead us to take on our calculator tangent of pi plus 0.1, 2, 3, 4, 5 zeros and 1 minus tangent of pi all over 0.000012340 So if you do that on your calculator, surprisingly enough, it comes out pretty clean to be 1. So that is our derivative. Now I'm going to ask a second question. Can we find, so the next question is, can we find an equation of the tangent line to f of x equals tangent x at x equals pi. So to find an equation of a line, we need two things. We need slope and we need a point. So our point is going to have to be a point on the curve. The x-coordinate is going to have to be pi, and the y-coordinate will be tangent of pi. Well, tangent, remember, tangent of pi is going to be sine pi over cosine pi, but sine pi is 0 and cosine pi is -1, so that's going to be 0. So our point is going to be pi 0. Our slope is going to be our f prime of pi. That is the derivative of the tangent evaluated at pi, which is what we just found right here. That is, in fact, f prime of pi. And so that's going to be 1. So the equation of our tangent line is going to be y minus 0 equals 1 times x minus pi, or with the minor cleanup, that is going to be y equals x minus pi. That's the equation of the tangent line. So I'm going to move to a new screen, and we're going to do some stuff algebraically. So we're going to find the derivative algebraically, or sometimes that might be called analytically. So those are kind of equivalent. So I'm going to put in parentheses analytically. So instead of using our calculator and plugging in a very small value of h, we're going to actually take the limit. And then after we do that, so this is going to be part A, and then part B, let's see if we can find an equation of the tangent line. Equation of the tangent line to that function at that point. Okay, so here's our first function. We're going to say f of x is going to equal 1 over x plus 2, and we are going to find f prime of 0. Okay, here's how we find f prime of 0. We're going to take the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. So f of 0 plus h means we're plugging in 0 for x. So that's going to be, I'll take the limit as h goes to 0 of 1 over, let's see, that's going to be 0 plus h plus 2. I guess that'll be h plus 2 minus f of 0 is going to be 1/2 all over h. Okay, how do we do this? If I direct substitute in 0, I'm just going to get 0 over 0. So the trick is I'm going to have to get common denominators. So I'm going to have to multiply the first fraction, top and bottom, by 2, and the second fraction, top and bottom, by h plus 2. So we're going to get a common denominator of 2 times h plus 2, and then we're going to get 2 minus, remember this minus has to distribute, so that's going to be a minus h minus 2. There's our common denominator, and we still have that all over h. And we're still going to take the limit as h goes to 0. So to divide by this h is going to be to multiply by 1 over h. So we can see these 2's are going to cancel. So we're looking at now the limit as h goes to 0. We've got a negative h over 2 times h plus 2, and we've got this 1 over h. that is going to cancel that. So we're going to get the limit as h goes to 0. That looks like -1 over 2 times h plus 2. And we can direct substitute in 0 for h, and that's going to be -1/4. That is f prime of 0, which we also know is going to be the slope of our tangent line at 0. We also need a point to get the tangent line. So we've done part A, so this is part A right here. Now for part B, we have to get a tangent line. We also need a point. So if we plug in our x value of 0 into our original function, that gives us a y value of 1/2. And so our tangent line is going to be y minus 1/2 is equal to, our slope, which we just said was -1/4 times, I guess that'll be x minus 0. Well, we can hardly resist cleaning this up a little bit. So y equals -1/4 x plus 1/2. Either of those is our answer to part B. So let's do another one. We're going to say this time g of x is going to equal 3x minus x squared, and our point, our x value, is going to be 2. So here we go. To find g prime of 2, we're going to take the limit, because remember this is going to give us our slope. We're going to take the limit as h goes to 0 of g of 2 plus h minus g of 2 all over h. Okay, here we go. That's going to be the limit as h goes to 0 of, and this is going to be 3 times 2 plus h minus 2 plus h squared. There's our our g of 2 plus h minus, and now we're going to plug in 2, so that's going to be 3 times 2 minus 2 squared, and that's all going to be over h. So that's going to be the limit as h goes to 0. Let's see, that looks like 6 plus 3h. We're going to subtract. Here comes our squaring that out. First one squared, twice the product, plus the second one squared. And that's going to be 6 minus 4, so that's 2. So we're going to get a minus 2 all over h. Getting there. So we have the limit as h goes to 0. We have 6 plus 3h. That's going to be a minus 4 minus 4h minus h squared. Still got the minus 2 all over h. So hopefully everything without an h is going to cancel. 6 and the -4 minus 2 kill each other off. And it looks like the 3h and minus 4h is going to get us a -h minus h squared all over h. And we're still going to take the limit as h goes to 0. So we can factor an h out, getting us -1 minus h all over h, still taking that limit as h goes to 0. Once the h's cancel, we now can say the limit as h goes to 0 of -1 minus h. We can direct substitute in the 0 for h, and that's going to be -1. That, remember, is g prime of 2, which is our slope. Our point is going to be, we're going to plug in 2 into the original function. So g of 2, I think we did that earlier, didn't we? So g of 2, I think we saw right up here, was going to be 6 minus 4 is 2. And so that's going to give us our tangent line is going to be y minus 2 equals -1 times x minus 2. We can leave it like that, is good for me. Okay, let's do one more tough one. We're going to say h of x is equal to the square root of x plus 4, and our x value is going to, well, let's say, yeah, we'll say our x value is going to be at 0. So our slope is going to be the derivative, I don't know if if h is a good, well, we'll use it anyway. So I'm going to have these h's in there that aren't the function, but we'll see if we can keep track of it. So h prime is going to be the limit as h goes to 0 of h of 0 plus h minus h of 0 all over h. So that's going to be the limit as h goes to 0. Let's see, if we plug in 0 plus h, we're going to get the square root of h plus 4 minus plugging in 0 will be the square root of 4 all over h. So that's going to get us the limit as h goes to 0 of, well, we're stuck with square root of h plus 4 for now. Square root of 4 is 2 all over h. Well, the trick to doing this limit, if you recall, is going to be to rationalize the numerator. So we're going to multiply top and bottom by the conjugate of the numerator. So we're multiplying by 1 in a strange form. That will give us the limit as h goes to 0. On top, we're going to get the difference of two squares, which will make that h plus 4 because we removed the radical. And then minus the 2 times 2 is going to be a 4. That's going to be all over h times the square root of h plus 4 plus 2. Okay, the 4's are going to kill each other off. Once they're out of the picture, now the h's are free to cancel. And so what we're actually doing is taking the limit as h goes to 0 of 1 over the square root of h plus 4 plus 2. Now we can direct substitute in the 0 for that h, which is going to be 1 over the square root of 4 plus 2, which is going to be 1/4. That is our h prime of 0, which is the slope of our line. Our point is going to have x-coordinate 0, and when we plug that into our function, 0 plus 4 is 4, square root of 4 is 2. That's going to be our point. That also happens to be a y-intercept, so our tangent line is going to be y equals the slope 1/4 x plus y-intercept b is 2. All right, see what you can do with homework 17.